Going on? So we're going to go over non-relativistic quantum mechanics and just the basic concepts of it. So we're going to derive it from one negative assertion, which is the non-existence or some fundamentally negative assertion is that quantum mechanics ultimately is going to declare that there is a non-existence of a trajectory, and then we need to necessitate mathematics that will then make everything consistent again with classical mechanics. Okay. So, in trajectory, I mean in the classical sense. So, we start with the uncertainty of the measurement of a particle in position space. What happens is when we do this, there's inherently some variance in the things that I could know naturally about its generalized velocity, or the generalized temporal derivatives of that coordinate. Okay, so if you can imagine this, the more and more that I try to resolve the single particle experimentally, the more and more uncertain I'm going to be able to tell about its velocities. And so, if you remember from classical mechanics, simply just this is the only classical mechanics we'll review. But basically, if I have some path between A and B, for me to know this with determinism and the Euler-Lagrange equations is to get the equations of motion for the accelerations that solve for this particular path. And this is called the principle of least action. It's whenever you allow for an arbitrary the space of arbitrary paths to exist, and thus, integrating by parts, taking the variation of it, it encodes with us the Euler-Lagrange equations must be satisfied for the maximal action. Okay, but this inherently, if we don't know, if we're uncertain about either one of these things, determinism is completely gone. We can't determine anything, or we can, but our concepts are only effective to the definite quantities. The effective definite quantities that we have on the classical system. And so this is the fundamental principle here. The uncertainty principle. Okay? The uncertainty principle just tells us that this classical trajectory cannot exist, okay, for a quantum particle or some quantum object. And so what we need to do now is define this quantum object. So we're going to start with something called an apparatus that is going to interact with these wave-like quantum objects. Okay, so this apparatus is classical. This is inherently classical. Okay, so the position and the momentums, the position and the velocities are well defined, and we can get equations of motion for the system. But what's happening is these quantum objects now that have these wave-like properties are then going to have to be inferred in some way when some change happens. Okay? When some change happens in that state, this is entirely how we're going to formulate quantum mechanics. We want some mathematics that is going to give us this. Okay? And this act of interaction is going to be formally called measurement. If you had a series of Stern-Gerlach experiments, where we observe this and, we denote things by probabilities and try to measure out different outcomes. We get strange results, but what's happening is with these inhomogeneous magnet systems, if you're familiar with this, inherently it's going to change the state once I measure it in a certain direction of that particle. And so what we need of that quantum object, and so what we need to do is formalize the mathematics for this. Okay? So we're going to derive this entire mathematical system which encodes this very idea of needing to extrapolate some quantum mechanical properties from classical theory from our known classical theories and some effective limit, okay? So we're going to start first with, we're borrowing a concept from differential equations. And this comes from the general solution for waves. And it is known that if we have some, I guess, let's call it psi, okay? This is going to be called a wave function, where Q is a set of generalized coordinates, okay? So generalized coordinates, okay? And dq is the volume element of those generalized coordinates in configuration space. Okay? Okay? In configuration space. And what this means is that this is a state, or this is a space of all possible locations that this coordinate could be at. Okay? And so this is a volume element of the system's configuration space. And so lastly, we're going to have the state of the system itself with some differential of that is going to be representative of the probability. It is going to be the probability of finding that system's coordinate. So finding that system's coordinate within the volume element of dq. Okay? So this wave function, the magnitude of the wave function, it should be the modulus squared of the wave function should be some probability of finding q in dq. Okay? So that's basically the setup here. And so this is going to have to obey something. Obeys something called the normalization condition. Okay? And the normalization condition just tells us that the squared modulus of the wave function of that state, integrating it throughout the entire configuration space, configuration space needs to be set to unity. Okay? And so this normalization condition is really important, because it's going to suppose us, or it's going to allow us to describe probabilities and fix that the maximum probability that something can have is 1. Okay? That's the use of that. And so the principle of superposition, obeying this, then gives us that the state should be able to be decomposed, as we know in differential equations, into the states that it could possibly take on. Okay? And so if a state is described by psi 1, but is also described by state 2, it can also be in any linear combination described by both of those states. Okay? So we can just add those functions to give us the final, or the actual state of that system. Okay? And so the last thing that we can do is just say, okay, well, if I wanted to describe some kind of non-interacting state, if there's a system of two parts, if I have two systems that are non-interacting, and they're not, their wave functions aren't bleeding into each other, or they're not entangling with each other, which we'll define what that is later, we can have that is the product of those wave functions. Okay? At those particular coordinates, okay? And so this is something that we inherently can do, all right? So now that we've kind of set up this idea of superposition, what we need to do is now define operator theory, okay? Operator theory is necessitated. It's a necessary kind of thing that we need, because these these states can take on multiple values, or they can take on take on forms that are of matrices. Okay? So we need to have something that is going to act onto the wave function, either differentiate it or do something interesting. Okay, and so for physical quantity, let's call this physical quantity F. We're going to refer to this from now on. Is for physical quantity, its measurable values are its eigenvalues f sub n. Okay? Its measured values are eigenvalues, denoted f sub n, of which this can take on a definite value. Okay? This can take on a definite value, fn, corresponding to its eigenfunction. Psi n. Okay? So the physical quantity can take on an eigenvalue corresponding to its eigenfunction. And this will look, the state of the system, of course, obeying the superposition principle. I'm writing that wrong, hold on. The state taking on the superposition principle can then be formulated in terms of its eigenfunctions with these coefficients, where we can say that the physical meaning of these coefficients, okay, where an is a probability amplitude, which we then define that the square modulus of this coefficient is then, of course, the probability itself. Okay? And so this would be the probability of the measuring the physical quantity f in the state of f sub n. Okay? This is a probability that's associated with this eigenfunction, that this associated eigenfunction will spit out this eigenvalue of this measurable value, okay? Or of this measurable physical quantity. Okay. And what this is then going to allow us to do is it's going to allow us to apply some of the normalization condition things that we defined before, which is that the sum of the probabilities must be set to unity in a discrete sense, okay? And so the coefficients then can also be set with this formula here, or they can be solved for with this formula, where we take the complex conjugate of the eigenfunction, okay? Take the complex conjugate of the eigenfunction with the state itself, and we can it'll spit out the probability of that eigenfunction actually kind of happening, okay? Or of us actually observing that particular eigenvalue, okay? And this requires some function, this integral here, to be true, which is that if I were to take the nth columns of the state and the nth columns for those particular eigenfunctions, okay, the nth conjugate of the eigenfunctions with this, this is in a more general sense, right? These would be some row and column vectors which correspond to the states, but this should be associated with something, this should be equal to the Kronecker delta. So okay, this should be equal to the Kronecker delta. And the Kronecker delta we'll define later, but or you can just look it up. But it's essentially going to give us unity. Okay, it's going to give us unity, and this is what we will call an orthonormal kind of set. Okay, so this is a more kind of matrix identification of unity, which should return that both of these are orthonormal in each other. Okay, and the orthonormal set means that it's self-conjugate. Integrated throughout the configuration space should return to us the Kronecker delta function. Okay, and so next we can define the mean value. So the mean value was kind of, if we wanted to take this idea of the quantity f, but we want the mean value of the quantity f, or the expectation value, which in statistics, if we had some ergodic process, it should give us essentially the expectation value, or the distribution should, the expectation value should emerge to that distribution when we take enough samples. Okay, so this is kind of a statistical meaning that we're trying to define. But the mean value, or the expectation value, will be defined as the sum of the eigenvalues. The sum of the eigenvalues times the probability. Okay, so just probability times the eigenvalues that this function can take on, or that this physical quantity can actually take on in nature. All right, and so then what we would have is that we can redefine this, the physical quantity for each physical quantity. So for each physical quantity f, there exists an operator. Okay, there exists an operator, and we can define it in terms of the mean value, where we have the complex conjugate of the state of the operator acting on the wave function here, integrated throughout configuration space, or the space of configurations that particle could take on. All right? And so this mean value gives us some definition of what an operator is. The operator is acting on this wave function, and such the mean value is this. So the actual definition of an operator is related to the expectation value, which is very important. Okay. The eigenfunctions. Okay. Let's erase this here. The eigenfunctions. Psi n related to those eigenvalues are the solutions to the operator equation. So for any eigenfunction with the physical quantity, this should be somewhat related to what I have up here when I'm defining the operator in terms of the mean expectation value. Okay? And so this kind of gives us some logical consistency with the theory that we're doing. And since the eigenvalues of the physical quantities must be real, we're showing that these eigenvalues have to be real, the corresponding operators must be what we call permission, or self-conjugate. Okay? And self-conjugacy satisfies this condition here, that for some wave function phi, okay, squared, or for some other state that we're introducing now, another state, with the operator acting on some state that we know, dq, this should be also equal. This necessitates the equality of this integral to be the operator acting on the complex conjugate of the quantity of this other state times, or convoluted with that other wave. Okay? And so, sorry, this is not really clear, but that's really what I'm trying to say. This has to equal this, and this is the definition of self-conjugacy. Okay? This is a purely kind of statistical idea. There's really the mathematics that's kind of new here is this idea of conjugation, self-conjugacy, and operators, and the operator equations satisfying this satisfying this operation on an eigenfunction, which will then return the relationship between its integral in the configuration space and the expectation value. And so these are all kind of this is basically the operator theory that is formulated that we need for quantum mechanics, right? It's necessary. It's not something which is not something that was just created for, for fun or for making things complicated. There's certain relationships that, that are formulated to express the basic ideas of this uncertainty, okay? Because essentially we're formulating the probability theory, which is going to come. So next we need to talk about continuous spectra. Okay? Continuous spectra. And so if we have a wave function here, we can actually expand it out in terms of those probability amplitudes associated with some physical observable. Okay? We can expand it out with some probability amplitudes with a physical observable integrated with respect to that physical observable. And so here, this is the probability that the quantity that f takes on a value between f and f plus df. And let's just call this f prime. Okay, so that it takes on a value, this physical observable, or this quantity, takes on a value between this interval. Okay? And so the normalization condition then is also, of course, we have to set that to unity for those coefficients. Nothing new. I'm sorry. Did I do this right? Yeah, I'm good. Okay, so now we need to define the expansion coefficients. And so we can actually solve for these expansion coefficients, which give us that the wave function if we were to take the states themselves, but we're taking the complex conjugate of the wave function associated with this integral here that we're extrapolating with respect to the state, and we can then have these this expansion, these expansion coefficients, and also express the orthonormality as such. So we would say that it's the integral of the complex conjugate of f prime, okay? Comes the complex conjugate of f q dq, all right? And this should be equal to something called the Dirac delta function, okay? Wherever we see that physical observable taking on some state between this f and some increment of that f, and if it takes on that state, then basically what's going to happen is that this value is going to turn into 1, or the integral, if we were to integrate this it would return unity. But if we were to be anywhere else, if this delta function were anywhere else, it would just go to 0. Okay, so you can think about this as kind of like a distribution. Okay, so basically, let's just say the Dirac delta function. So this Dirac delta, and the simple definition for this is if I were to, let me make sure that you can see. If I were to have the Dirac delta function is equal to 0 anytime that x is not equal to 0, and so you can see how I said that it shifts it, but essentially has the same property, and that the integral of delta x dx is equal to 1. Okay, you can't see that. Sorry. The integral of delta x is equal to 1. Oh, sorry, it's equal to 1. Or unity. Okay. This, the set of coefficients, f of a, or a as a function of f, okay? So a as a function of f, is called the wave function in the f representation. Okay? The wave function in a physical quantity representation. All right? And so this just as the wave function here, if we were to take the squared modulus of this, this will give the probability distribution for the coordinates, which we multiply then by the volume element of configuration space. The quantity here, this quantity here, gives the probability distribution for the quantity f. And hence, we have kind of this new description of continuous spectra that are observed from physical quantities. So we have it in terms of the probability of observing that physical quantity, and also the probability distribution. All right. Now, what's next is the limiting case of classical mechanics. So in the very definition of quantum mechanics, we had classical apparatus that then is being affected by some quantum object, which then was interacting and measuring. The active measurement is happening classically, and so what we have to do is extrapolate something from classical. But what we have to then prove is show that there exists some quasi-classical limit. Okay? There exists some quasi-classical limit. And so let's suppose that the wave function takes on the form of having some probability amplitude times some phase factor that depends on the action quotiented by some Planck's constant, where we define h bar, we call this h bar, to be Planck's constant divided by 2 pi, which is then just the quantization or the photoelectric effect when it happens, the slope of it, but then we're normalizing it by that phase that we need to make it useful, okay? And so this is a wave function that here we're going to say that this is a slowly varying amplitude, so basically a dot is approaching 0, and we're also going to say that h bar is approaching 0, and you want to work out that mechanically. Of course, S is the classical action. Okay, and it obeys the same kind of integration rule where we integrate the Lagrangian, the kinetic energy minus the potential energy of a system, okay, in arbitrary coordinates. And so if we were to set the variation of these guys, this would equal 0, all right? This is all of classical mechanics is here, and we're implementing it into this wave function, and we're going to take the limit for a and h bar, and if you compute this, which is not very hard to do, but basically what's going to happen is this phase, this wave function itself, is the phase is going to become very large, so that it follows essentially a classical trajectory. But what's happening is it's just a little bit fuzzy. But if we take the limit to be exact, and we localize all of the quantum mechanical properties into a classically assumed reality, we will then collapse it into the exact classical trajectory that we needed to resolve our initial discrepancy or initial non-existence of a path. They're just very localized wave packets now, almost like little delta functions that are traveling along the path. Okay, and so that's kind of the classical, quasi-classical limit. And so we kind of have this strange, interaction where the very definition of quantum mechanics will then be contingent upon the limiting case of classical mechanics. We're just extending it to Hermitian statistics and the statistics of self-adjoint operators. So, in order to make a measurement now, we need to define, okay, now that we know that we have some kind of consistent formulation with the wave function or the state of a system, its state in the configuration space, and we have the operator theory now to back us up, what we need to do is to think about something between some quantum object, okay? So some quantum object in Q coordinates, okay? And some classical object, or some classical system, let's just call it an apparatus again, okay? Some classical apparatus in C, okay? And what we're going to do is we're going to define, we need a model, okay? We need a new physical model of measurement, because before quantum mechanics there was nothing that was telling us what the physics of measurement was until we necessitated it for the interaction of these wave behavior of these particles, okay? And so what we need to do is say that the system will then start in some state, right, some quantum mechanical state here, and some classical mechanical state, all right, where this is the initial state of the apparatus. Okay? This is the initial state of the apparatus. Initial. Okay? The initial state of the apparatus. Okay? And so what we then need to do is say that there's an interaction. All right? There's an interaction between the quantum mechanical object and the classical mechanical object. And after interaction, the system will become entangled. All right? So the classical becomes entangled with the quantum, and the total wave function is a superposition over all the possible states or readings. Okay? It's the superposition of the possible states or readings that I could possibly have from this apparatus, okay, with new eigenfunctions that are functions of both the coordinates, or the probabilities would be the coordinates, but functions of the coordinates, or the readings would be a function of the coordinates of the quantum object, with the new eigenfunctions that are associated with the classical coordinates, okay? And so what this will then do is then allow us to take the entangled system, right, which we described as non-interacting first, then it interacts. We have an entangled system, okay, so this is an entangled system. Okay, the entangled system, and then what's going to happen is it's going to collapse. Okay, so what does it mean for something to collapse? For something to collapse, it means that the classical nature of the apparatus, it means that after the measurement, it is found in a single definite state psi in. And so it's found in psi in. It is found in a definite state after we measure it. All right? And so the sum, this entire sum here, will collapse into a single term, which is a function of the quantum mechanical interaction. So it collapses to a single term. All right? Single term A sub n of Q. All right? Okay. And what happens then is after this kind of interaction, and after we collapse it, it's in a new state. It's in a new post-measurement state. And so what happens is this is actually proportional. This is proportional to the electron's wave function, or some quantum object's wave function. It has to be proportional, and this will be redefined. So this will be redefined as some psi sub n eigenfunction of that quantum object. And this is the probability of obtaining the specific outcome, okay? The probability of obtaining this specific outcome as a function, of course, of the quantum coordinates is going to be, we ensure that the coefficients or the probability amplitudes also need to remain in unity and everything. And so this is the whole, hopefully this basically tells you that the collapse of the wave function is because it necessitates this classicality within the definition of quantum mechanics. All right? There's nothing confusing about entanglement, and there's nothing confusing about collapsing of the wave function. It's just conceptually it is strange. Conceptually we need a quasi-classical limit to formulate quantum mechanics, and we kind of fix, or we generalize the very problem that we're trying to describe in a statistical manner. And so the measurement is kind of this two-phased process. With respect to the past, right? With respect to the past, it verifies the probabilities predicted by the initial state of the system. Okay? And with respect to the future, okay? With respect to the future, it gives us a new state with a new set of eigenfunctions for that quantum system, and we have a new definite outcome from a probabilistic superposition, and this inherently is irreversible. This is an irreversible process, which establishes this fundamental difference between the past and the future in physics, all by introducing this new concept measurement. And so, what is the deliverable of quantum mechanics? I'll ask you, what is the deliverable of quantum mechanics? What problem did we just solve? Okay, if anything, okay, in your opinion, okay? I'll let you think about that for a second, and I'm going to write a board. I'm going to write a question on the board, which is how can a consistent physical theory, okay? How can a consistent physical theory be built for objects that do not follow deterministic trajectories? How can a consistent physical theory be built for objects that do not follow deterministic trajectories? We don't know with definition, we don't know with definite certainty the position or the generalized velocities, and so the principle of least action is ill-posed, okay? And so what we need to do is first, quantum mechanics, if you were to work within the Zen of Python, if you will, you know you're coding in Python if you're working within the Zen of Python. You know you're working within quantum mechanics if you are doing four things, which is first to abandon the idea of trajectories. Trajectories make no sense for quantum mechanical objects. There is no such thing as a trajectory for a wave unless it is in a certain quasi-classical limit. Okay? Second is to rely on a classical apparatus. Okay? We need to rely on a classical apparatus because without a trajectory, quantum objects or their quantum mechanical properties are not defined in isolation. Okay? And so in order to define them, we need to see their effect on the classical apparatus. And then we assign them values. To assign them values, the quantum object must interact with the apparatus described by classical mechanics. And then the third thing is to embrace uncertainty with probability. Okay? We embrace uncertainty with these probabilistic methods of measuring, of making measurements. All right? And so we have this strange idea of measurement collapsing a wave function, but it is simply just to recover because we are recover the classical mechanics because we are relying on this to define quantum mechanics. And fourth, the last thing is to introduce superposition. So quantum mechanics started with the idea of the non-existence of a trajectory. This classical notion of a trajectory doesn't exist because we can't know with absolute certainty the coordinates and the generalized velocities. But what's happening here is now quantum mechanics is adding something to physics now. We are introducing the idea of superposition of states. If a state can be, or if a particle can be in one state, and if it can be another state, those are two possible states that it can be in. It can also be in a linear combination of those states, and that is the superposition principle. And so basically it just says that interference then, this interference naturally leads to this mathematical frameworks where the states can be represented by complex amplitudes or wave functions that can be added, and the probability of an outcome is then proportional to the squared modulus, okay, of those corresponding amplitudes, okay. And so this line of reasoning is sequential and constructs the core formalism that states or quantum mechanical states now are wave functions in a linear space, all right? And the physical quantities are Hermitian operators, which satisfy those definition of Hermitiativity and self-conjugacy. And these are statistical kind of definitions. Then what happens is that we preemptively resolve many apparent paradoxes by rejecting the application of classical intuition directly to quantum phenomena, and instead we want to focus on the rules governing the interaction between those quantum systems and the classical world that we observe. So hopefully this was a good conceptual kind of rundown of the necessary concepts in quantum mechanics, and hopefully you saw that we started with a negative assertion, but we put something in place to replace it and allow us to then create this new, or not just create this new physics. Physics isn't created, but to formalize it, to formalize what's happening in nature from an abstract kind of level that is derived from the negative assertions. So thank you for watching, and hopefully you'll stay around for more. But yeah, peace out.